Okay, so draw the graph. The second is going to be interpretation from the graph. Interpretation from the graph. And the third is going to be interconversion of the graph. Okay, interconversion of the graph. Okay. So these are the three things that you should know about the graph. Okay. So for now, the drawing of the graph is an easy concept. Okay. The interpretation from the graph and interconversion are like interrelated. So we'll check both of them right together. But first we have to understand two things. The first thing is the number of quantities that we need to know in order to draw the graph. Okay, so the quantities are okay. So it can be current. Okay, and basically the current in the coil of electromagnet. This is the first thing. The second thing is um, magnetic field or the Hall voltage, okay, across the Hall probe, right? Across the Hall probe due to due to magnetic field, right? And the third thing is the magnetic field, okay, magnetic field, okay, or induced magnetic field or induced magnetic field. And the fourth quantity is the induced EMF, okay? Induced EMF, right? These are the four quantities we have, right? And we will be looking all of the quantities with respect to. So we will be looking every quantity against time, okay? And to understand the relationship, we first have to check their formulas, okay? So so formulas, okay. So uh, the first formula is B is equals to mu naught N I. Okay, this is the first formula. Okay, it is basically not the part of the syllabus. Okay. Okay, by the way, did I tell you guys what is that permittivity. Nope. Okay. So this is the first formula, okay? So this formula is basically related with a current. This is not a part of the syllabus, right? Whenever they gave you a question based on the coil, they'll mention the formula, okay? And not this formula is also not in the booklet of your paper, okay? Or the given formula sheet of the paper, okay? So this formula is for the uh, magnetic flux density uh, generated generated in the coil due to so magnetic flux density generated in the coil due to current flow through it. Okay. So this is a concept, right? Imagine you have a coil. Um, Imagine you have a coil, okay, and this coil, and there's a current in the coil due to the battery, okay. So the EMF or the magnetic field generated by the coil will be given by this equation, right? The equation I mentioned, okay. Again, this like the formula is not a part of syllabus, okay. So whenever they give you or they want you to use this formula, they'll mention, okay. Actually, by the way, mu naught, just know the concept of the mu naught. Uh, this is what we say permeability, permeability, ability. Okay, so it is basically the mu naught. Okay, um, like the permittivity of the free space for the electric field. Um, okay, we have the permeability of the free space for the magnetic field. Okay. So it is basically it is a tendency of a medium or better to say magnetic material, okay, or magnetic material to let the magnetic field lines move through it, okay. Okay, so this is basically the permeability, okay, through it. And this is the concept of the permeability, right? So if you have the wood is not a magnetic material, so it won't let any magnetic field line to pass through it, right? But iron on the other side is a magnetic material. So when there's a magnetic field generated, iron will absorb all the magnetic field line, and it generate a huge, or it generate a strong magnetic field around the core, around the iron, right? So like the property of the iron basically makes the iron to be a good magnet if you are applying some magnetization process on it, right? So acha. So iron iron has high permeability, okay. By the way, the mu naught has a value of 4 pi into 1 exponent negative 7. Okay, this is the value of the permeability. Um, Henry per meter, I think. Henry per meter. This is the unit. Okay. Now, so basically over here, the thing that I want you guys to know is the permeability concept. Okay, and this is a concept, and this value will be given in your first page of the exam, right? So by the way, this formula basically relates the magnetic field and the current directly, right? So like if you have the magnetic field, if you have the current, and the graph of the current is given as well, right? Like if you have the graph for the current is given, okay. So the graph for the current is given like as I in amps and T in seconds. Okay. And the shape of the graph is like that. Okay. So wait, let me just make it a bit smaller. Okay. Yeah. If I have a graph like this, okay, and I want to make the graph for the magnetic field, right? Because we know that the current and the magnetic field are related. Okay, so if I try to draw the magnetic field graph with respect to current, okay, and the magnetic field is basically into the coil. Okay, so B in Tesla. Okay, so the magnetic field graph will be like this. Okay, but both of the graph will have the same shape as you can see. B is directly proportional to I, right? But B would be slightly higher because B is getting multiplied with two constant to sorry, I is getting multiplied with two constant to get the value of B, right? So that's why it is like a bit like longer than the previous one. Okay, so you have to say same shape. Okay, so this is the first thing, right? Now if you have the hall prop or the hall voltage, okay, so you know that. Mm. Fine, fine, fine. Okay.
Sir,
Mm-hmm.
could you scroll better? Uh, this
Mm-hmm.
mu naught,
Yeah.
the units, what is that? HM minus
Yes.
1.
It's
What?
basically Henry per meter. Again, the unit is not required. You don't have to. You don't need to remember it. Okay. They'll give you in the exam. Okay.
Okay, sir.
Okay. By the way, it is Henry per meter. Okay. Okay. The anything related to permeability is not required. They'll give you everything in the exam, okay? If they want you to like figure out the value or like whatever. So fine. So the next thing, the next formula is basically the hall voltage. Okay. The hall voltage. Okay. So hall voltage. Okay. So so if you talk about the hall voltage, so hall voltage has a formula VH is equals to BI over BI over NTQ, right? This is the formula for the hall voltage, right? And this formula will also be given in the exam, okay? This one and this. Acha, by the way, this formula will be mentioned in the front page of the paper, right? But this formula won't be mentioned. I don't think so this formula is mentioned in the front page. Okay, they'll give you in the question if they want anything to solve regarding this formula. Okay. So fine.
But isn't that formula out of syllabus?
Yep. Like the understanding or the calculation regarding this formula is not a part of syllabus. Like they will not expect you to use this formula from yourself. Okay. Huh. If since you know the basic concept of magnetic field, current, and mu naught, okay, so they'll mention this formula and they'll ask you to use this formula, okay, and they'll give you the values as well, right? So you just need to put in the value and find out the value of the B, right? Or like any other unknown, right? Right? But
Yeah.
like anything regarding like the derivation or the other concepts regarding this formula is not required at all. Okay. Okay. So basically, for the Hall voltage, this formula is actually part of syllabus. Okay, and you don't have to remember it. By the way, they'll mention the first page of the paper. Okay, and over here, by the way, this is T. Okay, which you need to know. This is T, the thickness, not the time. Okay, the thickness. Okay, and the I is the current, B is the magnetic field. The simple thing, right? Acha, this formula relates the Hall voltage in the magnetic field. Okay, so Hall voltage um, generated generated ted when the current flow through the um, where the current flow through the semiconductor. Okay, when the current flow through the semiconductor, which is placed which is placed in external magnetic field. Okay, so the Hall voltage is basically generated when you have the current flow through the semiconductor, and when that semiconductor is placed in the external magnetic field. Okay, and for the sake of like understanding or memory, I can just bring this thing for you right here. Okay. Okay, so basically I have fixed. This is the Hall probe, by the way. Okay. This is the flat surface which I am calling out as a semiconductor. Okay. Face of, come on, flat surface of semiconductor, flat surface of semiconductor. Okay, we have two magnets. Okay, and there will be current flowing through it. Okay, and that induces the EMF, or that basically generate the cross field. Okay, for the semiconductor placed in the external field. Okay, actually, yes, it is just I'm writing this sentence just to uh help you remember this concept. Okay, the cross field, the cross field in the semiconductor conductor causes the potential difference to be created. Right. So this is a concept, right? So you can see that BH is directly proportional to I, right? And directly proportional to B, right? So if I have the Hall voltage graph and or if I have the magnetic field graph and I want the Hall voltage, right? So I can use like it will also be the same shape, right? Right. Okay. Right. So if I have the graph of V, oh sorry, B against T, okay, and the graph looks like this, okay. So I, sorry, not I, VH, like the whole voltage against against T, the whole voltage B against T will also be like that, okay, will also be like that. Mm, like both will follow the same shape, okay. Okay. Now, the last thing, and that is the induced EMF. Okay, so mm, okay, induce EMF. Okay, so the formula for the induced EMF is EMF induce is equals to the negative sign for the Lenz law. Okay, and BAN with a change sign over delta T. Okay, and sine theta. Okay, that most of the students call out as the band time formula. Okay, so okay, and over here on the top we have the magnetic field area and the number of coil or the number of turn for n. Okay, so and the delta t represent the time. Okay, the change in time. Okay, now for this you can, which picture you can use for the EMF induce. Wait, let me see which one I can show you for the induced EMF. Hmm, I think this works, right? Yep. Okay. So basically over here, this formula show you uh, okay. So induce EMF generated in the coil due to change in change in the magnetic flux linkage cage of the coil. Okay. So you have the magnet, okay, and you have given the coil. Okay, this is basically the coil. Okay, and as you move the magnet through the coil, okay, so that causes the magnetic flux to change. Okay, and due to that your EMF induced. Okay, so due to change in the magnetic flux linkage of the coil, which induces, sorry, which induces EMF in the coil. That's it. Okay. So if you want to draw the graph for the induced EMF and the magnetic field, okay. So now you can see that the magnetic field B over T, right? Like if you just pick this thing, right? So you have the rate of change of magnetic field giving you the EMF induced, right? So if I have the graph for like the magnetic field, okay. Wait, okay. So if I have the graph for the magnetic field, okay, and I am interested in drawing B, which is the magnetic field graph versus T, and induce EMF induce versus T. Okay, so let's say the graph for the magnetic field looks like this. So the induced EMF graph would be the gradient of this one. Okay, so it will be the gradient of the first graph. Okay, gradient, right? So just keep in mind that. Okay, now. So basically, this is how you can interconvert the quantities. Okay, so like if you have okay, if you have did we complete the yeah, three graphs? Okay, so if you have the current graph, okay, so that current can produce the magnetic field, okay, in this coil, okay. But if you have, let's say, another coil beside it, okay, so there'll be the EMF induced or the magnetic field induced in it, okay. So the induced magnetic field follow the same graph, okay, and induced EMF would be like that. The induced EMF would be the gradient of the magnetic field graph, right? So you can relate everything out together, right? So that's it for the whole chapter. Now let's try to do some of the questions regarding the graph and the calculation. Okay, let me take you to electromagnetism. Do I have it? Yep, right here. Okay, we have done some of the graph in the class as well. So, let's try some more questions on the graph. Okay, let's try this one. Do you see MF? Okay, okay, okay. Okay, Irfan, can you please read the question from the part B? Wait,
So which question?
on the part B.
Okay. Diameter of the cross section of long solenoid is 3.2 centimeters as shown in figure 9.1. A coil C with 85 turns of wire is wound tightly around the center of the solenoid. The magnetic flux density B in Tesla at the center of the solenoid is given by the expression B is equals to pi into 10 to the power minus 3 into I, where I is the current in the solenoid in amperes. Show that the current of 2.8 amp in the solenoid. Show that for a current of 2.8 amps in the solenoid, the magnetic flux linkage C is 6 into 10 to the power minus 4 Webers.
Okay, so basically, for the magnetic flux linkage, you do uh, wait a second. So you do BAN, okay, because BA is just a magnetic flux, and multiplying with N gives you the magnetic flux linkage, okay. So B can be find out using this formula, which is pi into 1 exponent negative 3, okay, into I is given as 2.8, okay, And then you have the diameter 3.2, right? So radius become 1.6, okay? 1.6 pi, okay, 1.6 exponent negative 2 squared, okay, into pi, okay, pi r squared, right? And n, the number of turns is 84, 85, okay? Okay, so multiply them all, please. Yes.
I'm getting 6.01 into 10 to the power minus 4.
Okay, good. So 6.0 exponent negative 4. Okay, this is what they're expecting us. Okay. Okay, please move on.
The current I in the solenoid in B is reversed in zero point 0.3 seconds. Calculate the mean EMF induced in coil C.
Okay. So to find the mean, you just need to divide the two. Okay, divide that by two. Okay. So induced EMF is equals to change in magnetic flux linkage, change in magnetic flux linkage, okay, divided by delta T, right? This is the formula that we use, right? So we found out the magnetic flux linkage, okay, like the change in the magnetic flux linkage. Okay, you can put it in, right? 6 exponent negative 4 and divided by 0.3. Okay, how much?
2 into 10 to the power minus 3.
Okay, so 2 exponent negative 3. Okay, um, mm, mm, mm.
So is that
And
delta phi?
delta phi n, yes,
N is the number of coils, right?
yes,
Turns.
yes.
But we didn't multiply that.
Bro, over like in the previous part we did everything, na? So BAN we did everything. So this is the 85 turns that we multiplied, right?
Oh, okay, fine. Yeah.
Okay. So by the way, to find like the mean induced EMF when you're reversing the current, okay? So you have to multiply your answer by 2 to get the final answer, right? If you don't reverse the current, there are two possible scenarios by the way, okay? So one is if you are reversing the current, okay? This is the first case. So for the final answer you have to multiply the answer by 2, and if you change the current to 0, then you don't have to multiply it with anything, okay? So that is one thing to keep in mind, okay? So due to that you'll get 4.0, and since the answer is in millivolts, so you don't have to write exponent negative 3 anymore, right? Is that clear? Okay, now let's move on to this part. Okay, so you have the current graph given, okay? So the current I in the solenoid is now okay, and they're asking you to show the variation with time t of the induced EMF, right? So you know that the change in the current, okay, the change in the current in the coil generates the induced EMF, okay? So And we know that if you relate, so EMF is equals to BAN over T, right? We know this formula, right? And since it is a coil, and the formula I've told you guys that whenever they give you the coil, they'll mention the formula. Okay, so you have this formula. Okay, just put that formula in here. In place of B, you have that constant pi exponent negative 3 times I. Okay, pi into negative 3 times I, and then A, and then N, okay, and divided by delta T, right? Divided by T, right? So you can see that the change in current, okay, the rate of change of current basically generating EMF, right? So, in short, you have to find out the gradient of this graph and you have to draw it here. Okay, this is the concept, right? Because the change in current I with respect to T gave you the EMF, right? According to this formula. Okay, so in these three portions we don't have any change. We don't have any change. Okay, so it will be zero right away. Okay, so in this portion, okay, and wait, in this portion, okay, okay, and in this portion. So basically, these are the three portions. So starting from zero to somewhere here, okay, first portion to be zero, and then zero point 0.6 to 1, zero point 0.6 to 1, another portion that should be zero, and then from 1.6 onward till the end, this should be zero, right? Now, these are the 2 points where you have to work out for the gradient and you have to draw the EMF, right? And you can see that we don't have any axis labeled on the vertical axis, so you don't have to find out the exact quantity or exact value, right? You can just wait, let me they're saying 4 marks, okay, so will they give you mark for that? No, I don't think so, don't worry. So you don't have to be you don't have to be like precisely draw the graph, okay, but you have to show that this is the positive gradient, okay, and due to the Lenz's law, the EMF induced would be negative direction. So sorry, this is a negative gradient by the way, negative gradient, and this is a positive gradient. So the negative gradient or the negative change bring the positive induce EMF, okay, and the positive change bring the negative induce EMF according to Lenz's law, right? So it will be like that, okay, like this, okay. This peak would be higher, or like this bar would be higher, and this would be lower in size, right? Because yep, okay. So because this gradient is lesser than this gradient, and we are supposed to draw the gradient, right? Is that clear, guys? Okay, channel. Force, you don't have to draw the force. Okay. Again, you have given the current graph and they're asking you the induced EMF graph, like it will be solved according to the previous question that we have done. Okay, again, the flux equation is given. Okay, and let's do one more question, then we'll end the class. Okay, Ibrahim, can you please read the question? Okay, this part B.
Coil of wire has 160 turns and diameter 2.4 centimeters. The coil is situated in a uniform magnetic field. The flux density 7.5 MT as shown in figure 9.1.
Okay, fine.
The direction of the magnetic field is along the axis of the coil. The magnetic flux density is reduced in a 0 of to 0 in a time of 0.15 seconds. Show that the average EMF induced in the coil is 3.6
Okay. So average induced EMF. To find the average when you have the magnetic flux density reduced to zero, okay, you use the formula induced EMF is equals to band tan. Okay, Acha, now if you have okay, you know that the B is 7.5 millitesla, 7.5 exponent negative 3, okay, and A is 2.4 diameter, so 1.2 radius, 1.2 exponent negative 2 squared, and then pi. That gives you the area, and for n, the number of turn is 160, okay, is 160, okay. Divide that by the time, which is 0.15, 0.15, okay. So this will generate you 3 point, okay, I think the answer is mentioned in front of us, okay. So 3.6 millivolts, okay. So this is the EMF induced, right? Fine. Okay, let's move on to the next part now. Yes. They, by the way, have mentioned the magnetic field, okay, and the magnetic field graph, okay, and they're asking you to use the data to show the. Now you have all the vertical axis value given, so in the graph you have to be very precise, okay. Now, the if you relate the formula, so EMF is equals to BAN over T, okay, over T, right? So you can see that the change in the magnetic field, the rate of change of magnetic field brings the EMF, right? A and N are the constant value, okay? So the rate of change of magnetic field brings the induced EMF, okay? So basically we have zero change here, zero change here, and zero change here, okay? So you can draw right away these sections, okay, from one, and then from this to this point, and then from this to onward point, it is like zero, right? Okay, so from 0 to 1, it should be 0 because the change is not there. Okay, from 2.1, 2, 3, 4, 5, from 2.5 to 3.1, 2, 3, 4, 5. Okay, from 2.5 to 3, 4, 5, from 2.5 to 1, 2, 3, 4, and 5. From 2.5 to 3.5 again 0. And then from 4.1 to 4.25. Okay. So 0.425, 0.412, and then 5. 0.425 to 0. Okay. So these are the three sections that we have now. For the two sections, okay. Acha, we know this one as 3.6 millivolts, right? Hmm. Same polarity. Okay. Okay, so for this one, we did the work, we did everything. So it is 3.6. Okay, so the induced EMF for this portion is going to be 3.6, right? So you can draw it directly. 2.2, 2.48, 3.6 right here. Okay, okay. This is the this is for the first one, right? You can see that both of them are of the negative gradient, okay. So I am drawing it in the positive section, right? According to Lenz's law, that would be the negative sign. That's why I change the polarity, right? And for this portion I have to work out, okay. So I can see that 0.35, okay, okay, 0.35 to 6, 7, 8, 9, 10, 11, 12, 12.25, okay. Basically 1.2 0.125 seconds, okay. So for this portion, the induced EMF would be 0.125 seconds, okay, for the time. And the rest of the things remain the same, okay. So you can copy out everything. Yep, we can copy out everything. Okay. So if you place, hmm, so 7.5 exponent -3 into 1.2 exponent, okay, into 1.2 exponent -2 whole squared into pi into 160 divided by 0.125. Okay. So, um, it is basically 0.425 minus 0.35. Okay. Sorry, it's not the correct one. You rather have to write 0.425 minus 0.35. Okay, so that gives you 7.238 millivolt. Okay. Induced EMF, right? Induced EMF. Okay, so again, it would be 6.247 would be like in between in the midway. Okay, and okay, so this is how this is how this graph should be formed. Okay, so now that's it. I'm stopping the class right here. We have completed the chapter. I'm sending you the password. You have to try, and I'll be taking the test of these three chapter in the next week, inshallah. Okay, so be prepared in the next week. Okay, the magnetism, electromagnetism, and induction. Okay, channel. Thank you. Okay, guys, take care. Nafis.